everybody. So, yesterday I taught you just how to find out a nonlinear evolution equation from a set of fluid equations which characterize the nature of plasma. I told you earlier that plasma can be treated or analyzed either of the two ways, either kinetic theory approach or fluid approach. So here we are considering fluid approach, or we discuss fluid approach, and just also inform you how a nonlinear evolution equation can be obtained from fluid approach. This equation 1 is the equation of continuity, which comes from conservation of mass. Here, since here in plasma, instead of conservation of mass, we can tell it conservation of charges. Ni is the, instead of density, Ni is the number density. Second equation, momentum balance or equation of motion, and third is the Poisson equation for charges. So to find out a nonlinear evolution equation, we generally follow few steps. First step is normalization. That is, we normalize the variables. Equation 4 shows you the standard normalization of plasma, which is discussed in the previous lecture. So after normalization, this equation 1, equation 2, equation 3. These three equations will be converted to equation 5, equation 6, and equation 7. Here, all the variable Ni, number density, Ui, velocity, phi, the potential, all are normalized. So second step is linearization. That is, if we want to find out linear waves, then we should linearize equation 5, 6, and 7 first. What are the nonlinear terms? Here Ni into Ui is a nonlinear term. Here Ui into del Ui dx is a nonlinear term. Here e to the power phi is a nonlinear term. So just we consider an equilibrium position where there was no velocity, no potential, number of electrons and number of ions are same, that is Ni equal to 1 and phi equal to 0. So equation 7 Poisson equation equal to 0. It was an equilibrium position which is considered. And then we consider a small perturbation on that equilibrium point, so that from the Ni will be changed from 1 to Ni bar, Ui to Ui bar, and phi to phi bar. So now putting this value of Ni, Ui, and phi, we get new set of equations. And this is the new set of equations, equation 9, equation 8, equation 10, and equation 12. So from in equation 8, if we remove the nonlinear term Ni bar Ui bar, we get equation 9. In equation 10, if we remove Ui bar del Ui bar del x, we get equation 11. And similarly, just expanding it to the power 5, we get equation 12. Next step, Next step, we want to find the relation between omega and k. Any wave, any sinusoidal wave can be written in the form sine kx minus omega t. K is the wave vector, omega is the frequency. So instead, since it is easy to calculate exponential function than sine function or cos function, so instead of taking sine kx minus omega t, for wave we generally consider e to the power I into kx minus omega t, because cos and sines are nothing but real and imaginary parts of e to the power kx I into kx minus omega t. We assume that all these Pater quantities, that is ni bar, ui bar, etc., all these Pater quantities are oscillate sinusoidally. This is an assumption. And accordingly, we write equation 13, 14, and 15 for n bar, u bar, and phi bar. So if we take derivatives of n bar, u bar, and phi bar with respect to t or x, we get equation 16, 17, 18, 19, 20, and 21. You can see that del n bar del t will become minus I omega into original n bar. Del phi bar del x equal to ik into original phi bar. So it's like that del del t may be replaced by I omega, del del x may be replaced by ik, and del 2 del x2 may be replaced by ik whole square, that is minus k square. So putting all these values in this equation 9, 11, and 12, we get three algebraic equations, 22, 23, and 24. These three equations where n0, u0, and phi0, they are three unknowns. So three equations, three unknown. It may be written in the form of matrix form, that is ax equal to b, where x is the column vector n0, u0, phi0, and A is the 3 by 3 matrix. So generally u0 equal to 0, n0 equal to 0, and phi0 equal to 0. They are the trivial solution of this system of equations 22, 23, or 24. But we are searching for a non-trivial solution. So the condition under which we get a non-trivial solution is that determinant A equal to 0. So this is the condition 25. So this condition gives a particular relationship between omega and k. That is, if we want to really find out a wave solution, linearized wave solution for this system, then omega and k should satisfy this particular relationship. Otherwise, we will not get linear waves. So this relation is called dispersion relation. So from this dispersion relation, we can write omega as a polynomial of k. If we again, we know that for a wave, the phase velocity or velocity of the phase is written by omega by k, which is a function of k and in the form of 27. And the group velocity is d omega dk. This is again a function of k, which is given by equation 28. In wave propagation, group velocity is much more important than phase velocity, as energy moves with the group velocity. So it is seen that if k tends to 0, then phase velocity and group velocity become same. And phase speed will be 1. But one thing we should remember here, that since phase velocity and group velocity are different and depend on k, so the system is dispersed. So since in a nonlinear system we are getting dispersive wave, so it's our legitimate demand to find out whether there is a balance between nonlinearity and dispersion or not. So let me see the phase. Initially it is omega equal to k, but in linear terms. But if we consider more nonlinear terms of this R series, we get omega equal to k minus k cube by 2. We may consider k to the power 5, k to the power 7, etc. terms. But okay, we assume also that k is small, not greater than 1 at least. So what is the phase in this case? We know that our phase is kx minus omega t. So kx minus omega t can be written in this form: k into x minus t plus half k cube t. So in equation 30 we have two different terms. One is k into x minus t and another is k cube into t. Since both are equivalent to kx minus omega t phase, so both of them have same dynamic status, at least dimension wise. So dimension wise, k into x minus t and half k cube into t, this should be same. So as in our consideration, k is small. As k is small, so let us assume a small epsilon such that k equal to epsilon to the power half. So if k is epsilon to the power half, then epsilon to the power half into x minus t and epsilon to the power 3 by 2 into t, both of these two terms have the same dynamic status. So x minus t means it shows a traveling wave. It's a traveling wave form in time t. Say traveling wave form depend on x and t, and it is completely the time t, the second term. So accordingly we consider two stretched coordinates instead of x and t, since dynamically x minus t and k cube t, k into x minus t and k cube t are equivalent. So for k into x minus t, we have chosen a new stretched coordinate xi, which is epsilon to the power half into x minus lambda t, and another is tau, which is epsilon to the power 3 by 2 into t. Now, so accordingly, all our fluid equations will be converted, can be written in the derivative of xi and tau instead of x and t. And we also consider, so we also consider that all the variables ni, ui, phi are also can be written as the power series of epsilon in the neighborhood of the equilibrium point. So what is the equilibrium point position? 1, 0, 0. So we expand all these things in the neighborhood of 1, 0, 0, and we obtain equation 32, equation 33, and equation 34. Again, since we want to convert del x and del t, we want to replace del x and del t by del xi and del tau. So we got equation 35, 36, and 37. Del x will be replaced by epsilon to the power half del xi. Del t will be replaced by this. Del x2 will be replaced by this. And accordingly, equation 5 to 7 can be written in as equation 38, 39, 40. 5, 6, 7 will be 38, 39, and 40. Now, we want to substitute this equation 32, 33, and 34 in 38, 39, and 40. And accordingly, we get, and we just collect the lowest order of epsilon, we get equation 41, 42, and 43. Now we integrate equation 41 and 42, considering that all the variables tends to 0 at xi tends to plus minus infinity. And we get the relation between n1, 1, ni1, ui1, and phi-i1. Three equations, three unknown. System of homogeneous equation can be written in the form of ax equal to b. Condition under which it has a non-trivial solution is determinant a equal to 0. And that condition gives not lambda square equal to 1. So this is the phase velocity. So this lambda, what we have considered in equation 31, it should be plus 1 or minus 1. Here, equation 31 shows clearly that lambda is plus 1 or minus 1. So from first order of lowest order of epsilon, we get the value of lambda. What is the speed? Phase speed. Next, we want to find out the evolution equation. To find out evolution equation, we consider next higher order of epsilon. And considering next higher order of epsilon and doing some mathematical manipulation, we get a nonlinear partial differential equation 51, which is the famous Korteweg-de Vries equation or Kdb equation. The first term is the evolution term, which shows how phi1, the first order perturbation of phi, evolve with respect to time. The second term, phi1 del xi, is the nonlinear term, and the third term, del 3 phi1 del xi3, is the dispersion term. It is observed by Korteweg and de Vries in 1897 that a fine balance between nonlinearity and dispersion have given birth to a particular type of wave which never ceased nor dissipate, rather moved infinite times, keeping its shape intact. Such waves are called solitary waves. So, we considering a new variable, independent variable, eta equal to chi minus u0 tau, and end up have done some integration. It can be shown that the solution of 51, a traveling wave solution of 51 will be phi 1 equal to phi m sec hyperbolic square eta by delta, where phi m is equal to cu0. This is the amplitude of the solitary wave. This delta is the width of the solitary wave, and u0 is the velocity of the solitary waves. It is clearly seen that if u0 is the velocity, then cu0 equal to amplitude, and 1 by root over u0 is the width. So the velocity, width and amplitude can be written in a single parameter. In figure 1 shows a typical shape of a bell-shaped type solitary waves. In next problem, what I have explained also, that the equation is same. Instead, in equation 54, that is in equation of motion, we consider an additional term minus nu yd into uy. This is the collision term, friction type term, collision between ion and neutral particle. So we want to find out what is the effect of this term on the solitary waves. Sometimes dust are considered in plasma, and if such teeny dust have some collision with the ions, then this nu yd is the dust and collisional frequency. So if in a dusty plasma, there is plasma in presence of dust, the same model, the same ions are moving in the background of electrons, and the ions made little bit collision with the dust. Then what is the effect of this dust and collision on the solitary waves? So procedure is same. Normalization, finding out the value of lambda, that is phase velocity, and we obtain a particular equation which is called damped type Kdb equation. Del phi 1 del t is suppose in 61 right hand side is 0. So this is the standard Kdb equation what we have obtained earlier. This last term C phi 1 came because of the dust and collision. As C equal to nu id0 by 2, and nu id0 is the dust and collisional frequency. If instead of this, we have taken some source term or forcing term on the right hand side, be del s to del xi, then this equation 65 is called damped forced Kdb equation, or DF Kdb. First three term for Kdb, first term for damping, and this right hand side term for forcing. Damped forced Kdb equation. Now we know the solution of the Kdb equation, but how do we find out the solution of the damped forced Kdb equation? A natural answer is by numerical computation. Yes, by numerical we can do, but since it's a nonlinear higher order partial differential equation, doing any numerical needs a huge computation and chance of a large computation error which may not be controlled So accordingly, we are searching for a nonlinear approximate analytical solution of this nonlinear equation. Suppose this is the equation 62 is the damped force Kdb equation. A particular form of the force is considered F0 cos omega tau. In absence of C and F0, that is in absence of damping term and forcing term, equation 62 converted to the standard Kdb equation. And the solution will be phi 1 equal to phi m sec hyperbole square chi minus m tau by omega. Now, we want to find out an approximate analytical solution of equation 62 by some trick. The trick here we use is the conservation of some properties of the Kdb equation. The Kdb equation is very famous and well studied as it preserves an infinite number of conserved quantities. One such conserved quantity is integration minus infinity to plus infinity I squared design is conserved. Now we assume that the solution of 62 will be same form, the form of the solution of 62 will be same as 63 provided except that on phi m, and omega all depend on tau. That is, the solution of 62 will be in the form of 65. And this tau dependent terms is m tau, omega tau, and phi m tau. We have to find out, or we shall find out by using the relation 64. That is, I is conserved. That is, di d tau is equal to 0. So differentiating 64 with respect to tau and using 62, one can easily obtain equation 66. You can do it yourself. So accordingly, I can be calculated. There are two ways by which we can find out I. One relationship is di d tau plus 2ci equal to 24 f0 root p by a root over m tau cos omega tau. And that is this. So from these two equations, 66 and 67, equating these two, or not equating, solving this and putting the value of I here, one can easily find out the value of m tau. And m tau is obtained as this expression, m tau equal to this. Please check, if c equal to 0 and f0 equal to 0, then m tau is constant and it will be m. That is, the solution comes in such a way that if there is no damping and no force, then the solution directly, solution 68 converted to 62. So this result 68 is very much similar to that of 62, except that all amplitude, width, and velocity depend on tau. So accordingly, pictures are drawn. You can find out how it changes on time t. Next, let us derive damped Kdb equation. In this case, instead of considering a damping term on the right hand side of 70, we also consider another term, eta del to u del x2 on the right hand side, where eta it is the dissipation term, eta del to u I del x2. So let us see the effect of nu it and eta both on the solitary waves. The normalization is done similar to that of the previous case. Perturbation is accordingly, except here we consider eta as epsilon to the power half eta 0 and nu it at the order of epsilon to the power 3 by 2. Doing the same way as we have done earlier, we got the value of lambda equal to 1 by root over 1 minus mu. And ultimately, the nonlinear evolution equation comes as del phi 1 del tau plus a phi 1 del phi 1 del xi plus b del 3 phi 1 del xi 3 plus c del 2 phi 1 del xi 2 plus d phi 1 equal to 0. The first term is the evolution term. It shows the evolution with respect to time. Second term is the nonlinear term. Third term is the dispersion term. Fourth term is the dissipation term. And fifth term comes due to dust ion collisional term. This C equal to minus eta 1 0 by 2. It comes due to kinematic viscosity. So suppose it is assumed that both C and D both are very, very small. Then our initial solution of soliton solution of 76 is considered as equation 77. And assuming the same procedure, that is the conserved quantity phi 1 square for the whole equation, Kdb equation, since this is the Kdb term, and if this is the Barcher term, so it is called Kdb damped Kdb equation. Okay. Solution may be obtained in this form where phi m, m, and omega depend on tau. The technique I have discussed earlier, and following the same procedure, we can easily find out the value of m will be m equal to pm0 by m0 q into 1 minus e to the power pt plus p to the power pt. It will be m, not m0. Not m, it will be m0. Just it is written as m. It's not m0, it's m we consider. For tau equal to 0, m equal to m. So it is a small printing mistake. So since m is known, we can find out phi m and omega since relationship is there. Phi m equal to 3m by a and w equal to 2 root over p by m. So since m is known, so all phi m amplitude and width of the solitary wave is known. Now, we want to derive another equation, what is called modified Kdb equation. This equation arises when, in a particular situation, suppose the nonlinear term vanishes, then what shall we do? The model is chosen same as that of Kdb virtual equation. Moving same as the previous way, we can obtain equation 90 as the damped forced Kdb equation. Here A equal to C 3 by 2 lambda minus B into lambda by A. That is, if 3A equal to 2B, then A vanishes. If A vanishes, then equation 90 is no longer a nonlinear equation because the nonlinear term vanishes and no feature can be extracted from equation 90. So we have to, if we want to study in that particular case where A is 0, then we have to find out some other technique or some other perturbation instead of other technique. We can find out some other perturbation scheme by which we can derive another equation. So accordingly, we have taken a different stretched coordinate j equal to epsilon into x minus lambda t and tau equal to epsilon cube t. It will satisfy the relation between omega and k of the first linear wave system. And if we consider nu id equal to epsilon q nu id 0, s is equal to epsilon q s2, then and proceed as we proceed earlier, we can obtain the equation same as that of damped force Kdb equation with a little change. Instead of phi 1 in the nonlinear case, here it's phi 1 square del phi 1 del xi. That is, the nonlinearity become cubic nonlinearity instead of quadratic nonlinearity. So this equation is called, instead of Kdv, we call it modified Kdv. So modified damped forced modified Kdv equation. To find an approximate analytical solution of 104, we proceed the same way and we can obtain the value of m equal to this. It can be seen easily that putting C1 equal to 0 and F0 equal to 0, m can be converted. M tau will be m. But for small c and small d, that is for in the presence of C1 and F0, the velocity, amplitude and width will be modified accordingly. This is the m, this is the phi m, and this is the omega. Whatever the equations we have done, we can do or we can study similar type of nonlinear evolution equations by reductive perturbation technique, and we can find out similar type of approximate analytical solution by considering the conservation principle of Kdb equation, provided the additional term which appeared to the Kdb equation are small. So here another equation we consider. All Kdb, all the equations what I discussed earlier are basically 1 plus 1 dimensional, that is x and t. But these results can be extended to 3 plus 1 dimensional, that is x, y, z, and t. So one such model is considered here. Equation here, just del and del t is same, and this is x, y, and z directions are taking. So equation 106 is the equation of continuity. Equation 107, equation 108, and equation 109. These are the equation of motion in x direction, y direction, and z direction. And equation 110 is the Poisson equation. Similarly, the normalizations are given by this way, and stretching is like this way. Here also chi, we need 3 plus 1 stage coordinate. Instead of 2 stage coordinate, we have taken 3 plus 1 4 stage coordinate. The perturbation is done as similar way, that is the dependent variables are perturbed from the equilibrium position. In the equilibrium position, n was 1 and u, p, w, and phi all are 0. We also consider the collision of the order of 3 by 2 and fourth term of the order of epsilon square. And accordingly, like the previous case, equating the lowest order of coefficient of epsilon and next order of coefficient of epsilon, we obtain lambda 2 equal to 1 by delta 2. And considering a higher order of epsilon, we obtain equation 131. See equation 131, the first part, it is same like the Kdb equation. D is the damping, so up to here first 4 terms give you the damped Kdb equation. This B is 2 delta, it is the force. So except this 1, 2, 3, 4, and 5, it is the, if we consider only these 5 terms, then it will be damped force Kdb equation. But 2 more terms appear in this equation, but 2 different directions, xi and eta. So C del del xi of del square phi 1 appears here. Because of these terms, this equation is named after damped force ZK equation. So this 132 is the damped force test ZK equation, which can be solved, or the approximate analytical solution of this equation 132 can be obtained. To do so, we have taken chi equal to this transformation L zeta plus m chi plus n eta minus u0 t. It was missing here. I'll tell you later. For L, m, and n are direction cosines of the wave propagation in direction x, y, z. So accordingly, the equation 132 converted to 134, and let's assume the solution of the form of 135. And if we proceed the previous way, considering the conservation of phi 1 square, phi square, then we can easily obtain the value of m. This is the m. Equation 136 represents the value of m, where phi m is equal to 3m by p and w equal to 2 into root over q by m. So in conclusion, we can say that some nonlinear evolution equations, approximate solution of some nonlinear evolution equations, are obtained with the help of the property of Kdb equation. Okay, so your task is to do all these equations. It's a book chapter written by myself, Lokikant Mandi, my scholar Kaushik Rai. my PhD student who obtained his PhD, and myself. So please go through the whole thing, do the calculations. If you find any problem, contact me, please. Okay? কোনো কোশ্চেন আছে তোমাদের?